And once those crystals are formed, you dry them using filter paper, you filter them out. Now, if I want the solvent, I got salt and water. If I want the solvent, what I'm going to do is I'm going to do distillation, and I'm going to do simple distillation. For this, simple distillation is, this is what it's going to look like. I'll just quickly add the apparatus. So now this here is the apparatus for simple distillation. You can remember you can be asked to draw this. So basically, you get a couple of questions on this. One of them is that the first part is that the water is going to evaporate. This image is not good enough. I'll just draw my own. So I've got a round bottom flask, and from that round bottom flask, I'll attach a Liebig condenser, which is simply going to be referred to as a condenser. Okay, so we're going to call it a condenser, and this condenser will have two openings. One of them is for water in, and the other one is for water out. Which one is for water in and which one is for water out?
Sir, the first one is for water out and the second one is for water in.
I mean, this one, what is this one for?
This is for water in.
Okay, this is for water in. You'll be asked to label this in a lot of questions. So cold water in, and the top one is cold water. It's going to be, that is for water out, because that's the only way the Liebig condenser is going to get filled up. So the cold water provides a cold environment. So the gas loses, or the steam loses energy. You got a thermometer that's placed right at the opening, and the top is sealed. So this top part is completely sealed, and you're going to heat it at the bottom. And if it's, let's say it's a normal salt solution, NaCl aqueous, so the salt particles would remain behind. They are not going to move. The water vapor would evaporate, and all the water vapors, they will travel to the other side. What will happen over here is that the gas molecules, they lose energy. And they're going to eventually condense. So that's the part where they're going to condense, and you're going to collect the water at the other side. What is the other name given to what is collected at the other side? What do you call that?
Distillate.
Yeah, that's referred to as distillate. Okay. Is Haris in the class? Just a second. Oh, just 1 second. Let me message. So, so that's referred to as the distillate, and the thermometer will help you figure out whether distillation is happening or not. Because remember, whenever there's a change of state, the temperature becomes constant. So the graph would kind of look like this. It's because it's got water in it, the temperature would initially rise, but then it would kind of become constant. And when it's constant, that means that basically indicates that the water, which is liquid. And remember, it could be any solvent, not necessarily water. It is changing state. It's changing into gas. So the thermometer at the opening is helpful because it's kind of a guide that will help you tell you whether distillation is happening or not. If it's a flat line, that indicates that the water vapors are going into the condenser. If it's not a flat line, if it's not the boiling point, then no distillation is taking place. The salt would just remain behind, and you can collect the pure water from the other side. So that's about it. So this is the point where distillation happens. Beyond this point, all the distillation has already taken place. Is that clear? Is this clear to everyone?
Yes, sir.
So anyways, now moving on. So that's all about this one. You don't get a lot of tricky questions on this. The next one is, what if we have a mixture of two liquids, miscible liquids? How do you separate them? And miscible liquids are liquids that mix with each other. So what do you have to do for that? Anyone?
Fractional distillation.
Yeah, that's fractional distillation. So you're going to use a fractionating column in that. So liquids that mix with each other. An example of that is ethanol plus water, that they completely mix. Or you can say vinegar plus water, that also mixes. Separation happens. Why? Because they've got different melting points. Sorry, boiling points. This one is 100. You don't have to remember this, but separation happens. Or for separation, for fractional distillation to work, they must have different boiling points. Separation happens because of due to different boiling points. And the apparatus would be exactly the same as distillation, except for an added fractionating column. So this is fractional this one is fractional distillation. So I'm just going to copy the whole thing, except so everything would kind of look the same. So except for this part, that over here there's going to be a fractionating column, and we're going to make just hold on 1 second. So we're gonna make a fractionating column over here in between. Or I can simply, what I can do is I can so the column has glass beads. It's got it's going to have lots of glass beads or anything, stuff that will increase the surface area. What's the purpose of the fractionating column? Why do you need a fractionating column? Anyone?
To make sure that only one liquid passes through at a time.
Okay, so the fractionating column, and here's the issue now. Now you've got two liquids. You've got, and both liquids can evaporate. You've got the red ones and the blue ones. So the liquid is mixed up of two molecules, two different molecules. It's got water and it's got ethanol. Now, ethanol has a lower boiling point, so it's going to evaporate quickly. While water has a much higher boiling point, it doesn't evaporate that quickly. So what happens now is when you apply the heat, remember evaporation, if it's 78 degrees centigrade, the ethanol will start to boil. And the ethanol molecules will start traveling. And what the fractionating column does is, it just makes it more difficult that the molecules to reach the other side. So for example, the ethanol molecules are boiling and they're trying to reach or get to the other side. So it's harder for them. So all these ethanol molecules, it becomes a lot harder for them to move past due to the extra collisions. It's very hard for them to move past them. But since ethanol's boiling point, ethanol will have sufficient kinetic energy to do that. But when ethanol is boiling, a few water molecules might also escape. Because remember, evaporation can happen at any temperature. So when this happens, a few molecules of water might also evaporate. Okay, so it might also evaporate. Now, the fractionating column is going to make it harder for the water molecules to reach the other side because it's not their boiling point. So the few molecules that do evaporate, they're going to bump into the glass beads and they would lose energy and they would eventually condense and they would fall back. So any molecule that evaporates and it isn't its boiling point, those evaporated molecules would tend to fall back into the container because they wouldn't be able to have sufficient energy to go past these glass beads. Is that clear, this part? Is this clear?
Yes, sir.
So you're going to write that what a fractionating column, the detailed answer for that would be that the fractionating column increases surface area. So it increases surface area and it makes it harder so if vapor gets contaminated by the higher boiling point liquid, so if it is contaminated by high boiling point liquid, those molecules would lose energy and they would condense back and fall back into the container. So the main purpose is that it increases the surface area. Because if they're going to ask you, so it increases the surface area and makes separation happen, it improves the separation. The higher boiling point liquid is not able to evaporate that easily, or at least go past through this through these glass beads. So that's the purpose of the fractionating column. The rest is pretty much the same. The graph for a fractionating column would kind of look like this. It's going to have the temperature would become constant 2 times. For example, if it's ethanol and water, it will rise first. Then ethanol will start to boil. And once ethanol boils, it will then start to rise again. And then at 100, it will become constant. And once all the water has evaporated, then it will start to rise again. So the temperature would become constant twice. Once at 78 and another time at 100 degree centigrade. So that is what's going to happen and what the graph would look like. Now, in fractionating column, there's a. So is this all clear? This part?
Yes, sir.
Okay. Just remember surface area. Molecules that whose boiling point has been reached, they would have sufficient kinetic energy to go past these glass beads and move to the other side. Molecules who have by mistake evaporated and it's not their boiling point, they would get stuck. They won't have sufficient kinetic energy to go past these glass beads. As anyways, what's the main application, big major industrial application of a fractionating column? Where is it used? Anyone, where's fractionating column used in industry?
The fractional distillation of crude oil.
Yeah, so the application is crude oil. So that's the major application. Crude oil is the black tar-like substance that is obtained from the Earth's crust. And it's a mixture of many different things, many things. Most of them organic, they're combustible. So you've got waxes, you've got petroleum jelly, you've got petrol. So you've got kerosene and you've got gasoline, which is the petrol that you add in cars, and so on. So many different things are obtained from crude oil. So so this is how fractionating column works in crude oil refinery. You got this big column, and this big column has many different trays, and it's got a vaporization chamber at the bottom where the crude oil is vaporized. Okay, so there's this tar-like substance that's entering, and let's see if we can have an image for this as well. So most of them are like I want to see an actual image. As anyways, we've got crude oil which is entering at the bottom, and this crude oil is completely is vaporized at very high temperatures. So that's at the bottom. That's your crude oil entering. And you've got very high temperatures, extremely high temperatures at the bottom. I don't need to remember the temperature, but the extremely high temperatures. And crude oil is vaporized. So everything that is present would, and then the vaporized sample is passed into this. It's passed into this big fractionating column. Now, all these vapors, they contain all sorts of molecules. They contain petrol, they contain diesel, gasoline, etc. Every other thing is present over here. So it's a mixture of many things, and all these molecules are mixed together and then in the form of vapor. Some of the molecules will not vaporize. So you have this tar-like drum, and this is what crude oil looks like. Okay, so hopefully I'll get an image of crude oil that's the image. So this tar-like substance, that's basically what crude oil is. This is what you obtain from the Earth's crust. It's in the sludge form. It's got many different things mixed together. So again, so basically you're vaporizing it. Now, most of the crude oil would vaporize. It would boil, and it will turn into vapor. But some of the stuff will not vaporize, and that's those are your residues that will settle at the bottom. And this residue is known as bitumen. Now that's what roads are made out of for. So you need to remember what are the uses of this stuff. So bitumen is the stuff that is used to make roads, etc. So for making for making roads. That's the first part. Now at the bottom, there's very high temperatures. Extremely high temperatures at the bottom. But as the vapor rises, it rises upwards. The temperature starts to drop, and the vapor would cool down as it moves upwards. It's going to, because at the top there's going to be low temperatures. Right? Is this clear? Aris, is this clear? I'm not sure. Is this clear?
Yes, sir.
Yes, sir.
So you got very high temperatures at the bottom. Now the substances that will condense, they all have different boiling points. Like you got kerosene, you got petrol, you got petroleum jelly, you got waxes. They all have different boiling points. Now, for example, waxes would cool off or solidify very quickly. So you got different trays. At the bottom, you got high temperatures. So in the first tray, you'll probably get a lot of, what you'll get is petroleum jelly. And waxes. That is what you'll get at the bottom, and that's used in many different places. It's used for, I mean, you'll get grease as well, which is, forget grease. So you make it, you use it for candles, you use it for car wax, etc. These are some of the uses for this stuff. Then the vapor continues to rise. So these particles, some of them will condense and they'll be collected over here. But the other ones, a lot of them would continue to move because their boiling point, they haven't cooled down enough. So they'll continue to move upwards. And the vapor would further cool down. When it cools down, there are further trays on top, which will collect whatever gets condensed at a slightly lower temperature now because it's cooling down now. So over here, you'll get furnace oil. Which is used for thermal power plants, power generation. So most of the power generation is done using this, and then the vapor will continue to rise. It will cool down further. There's going to be another tray that will be collecting the substances that get cooled down. So over here, you'll get diesel. I'll check the order right at the end. So diesel gets collected. Diesel is a fuel that's used in heavy transportation for trucks and for ships. Moving further up, the vapor goes further up, condenses again. Some other stuff gets condensed. This time it's kerosene. Kerosene and paraffin. Doesn't even know what kerosene is used for. Good idea. What is kerosene used for? It's got a very important use. Amna, Urva.
No, sir, I don't know.
So the kerosene is used for, it's jet fuel basically. Airplanes use it. So that's airplane fuel. So paraffin, kerosene, that's kind of the same thing. And then you move further up. More molecules they condense. Over here you'll get gasoline. Gasoline is the correct word of petrol. Petrol is a short for petroleum. Petroleum is crude oil basically. So petroleum is referred to as crude oil. We use the term petrol, which is incorrect because that's a short for petrol. I mean, the correct word is gasoline. Gasoline is obtained, and gasoline is basically car fuel. It's a more refined version of this. And then you're going to get naphtha as well, which is frequently used as small bunch of molecules that are used in the chemical industry to make medicines. And then right at the end, there would be some molecules that will not condense. Right at the end, there would be a few molecules in the mixture that would still not condense. And those are your gases. Those are your, so these ones at the top are known as your petroleum gases. And they're often used for domestic heating and cooking. So a lot of things are coming out of crude oil. So initially crude oil was this mixture of different molecules, different substances. It was this thick sludge-like substance. You took it to a high temperature, you vaporized it. Some of the stuff did not vaporize, and that's the black tar-like substance at the bottom. That's bitumen that's used for more roads. The vapor will travel upwards. It will start, its temperature will start to decrease. And every time the temperature decreases as it moves upwards, some molecules in the vapor will condense. Petroleum jelly waxes will condense over here. Furnace oil will condense. Then diesel will be obtained in these trays. The vapor will continue, and these are perforated trays. So the vapor could move upwards, and when it condenses, it falls into the trays. Kerosene, gasoline, naphtha, petroleum gases, all of this stuff. So you must know the order, and let me correct the order for once. I'll check what the order is just for. Just for confirmation, that's so that's waxes, lubricating oils, fuel oils. Usually in CIE, this is at the bottom. Just so the rest of the order is kind of correct. The bottom two, that's what we're looking for. Just 1 second. As over here, it's different. It's a fuel oil or furnace oil. Yep, this is the correct order. As anyways, this is written correctly. Furnace oil or fuel oil, there's another word for that. This is the lubricating fraction, that's petroleum jelly and waxes. So those are your lubricating fractions. So this is how the separation is happening. All the different molecules, they're getting separated because they have different boiling points. And some stuff that you have to remember also is that the stuff that gets condensed early on, that's the one that's got a higher boiling point. So the bottom ones, they've got a higher boiling point. So things that have higher boiling points, they will condense first. Like wax has a very high boiling point. Gasoline, the car fuel that you add, that's got a very low boiling point. So the top ones have a lower boiling point. So anything that's obtained at the top, it's got a very low boiling point. And the other thing is that at the bottom, you get large molecules. So these waxes, petroleum jellies, etc., they're big molecules. The top ones are small molecules. The petroleum gases, the cooking gases that you get, the car fuel, they're all small molecules. That's why they evaporate very quickly. So the top ones have low boiling points and they're also small. They are small molecules. Now you get a lot of questions on this, TK. So you just have to generally remember this, that crude oil is a mixture. You pass it through a fractioning column and the whole mixture gets separated based on its boiling point. The stuff that has a high boiling point, it condenses very quickly. Things that have very low boiling points, they don't condense. The ones at the top, they don't condense. Ye clear? Is this clear to everyone? Amna, RS, TK, no, is this clear? Now remember this stuff, and I'll just give you a brief idea, although you don't have to study organic chemistry right now, but I'll just give you a brief idea that when you've got, why is organic compounds important? Because most of the chemistry that's happening on planet Earth, it's happening. There's water that's important. Remember, water is one thing that's very important on planet Earth. The other thing is that we're all made up of carbon compounds. We're all carbon. All our molecules, living organisms, etc., plants, animals, humans, everything is made up of carbon compounds. Carbon is an atom that makes a lot of structures, a lot of molecular structures. Our cells, our skin, our hair, they're all carbon or carbon based. So crude oil is basically a lot of, it's fossil fuel. Fossil fuel is basically based on living organisms. So this is dead living organism. After billions of years, it turns into fossil fuels. So fossil fuels are also carbon-based fuels. So whenever you hear the term organic, organic simply means that it's got something to do with carbon. It's they're carbon compounds. Trees are organic, we are organic, fossil fuels are all organic, they're all made up of carbon. So when you're burning all of this, these are all carbon compounds, which is why they produce a lot of carbon dioxide, which is a greenhouse gas. So that's just some general stuff. So whenever you hear the term, from now on, whenever you hear the term organic, just remember organic or organic chemistry or organic compounds, it has something to do with living organisms. And it has something to do with carbon compounds. So this is stuff that you have to remember. Remember the order, remember some details about it, remember the uses of all of these fractions. And also remember this diagram, learn how to remember this diagram. What is the purpose of the fractionated column that you add over here? So that's the simple one. The crude oil example is a slightly more complicated one, which has a lot of stuff to remember. Okay, let's continue with this in the next class. So we're done with the fact, how do we separate two miscible liquids that mix with each other. So we figured out that they have different boiling points. You can evaporate one while the other one stays in the container. That's one way of doing this. Tell me a quick question, Dani. Is there any question about this? Is this fine?
Yes, sir.
Okay. Okay, let's make sure you're done with the assignment, okay, which I posted. Let's continue tomorrow then, and we'll try to finish this chapter. Then we'll do some past paper questions. Okay, everyone.
Okay, sir. Allah Hafiz.
Take care. Allah Hafiz.